Efficiency Research Fellow at Oxford University. Before this, I did a postdoc at Bristol University. And the talk I'm going to present today is on basically the work I've done at Bristol on small-scale testing of nuclear graphite. So basically, my talk is I'll say a few words about the background of the work, and then I'll introduce the technique I use for this small-scale testing. I'll focus on the materials that have been tested because I realize not many people actually are familiar with graphite and carbon-related materials. Finally, I'll say a few words about the recent development on this type of testing. Well, you can see that I listed 4 different types of materials here. One is the carbon, and the other 3 are graphites. And these 2, carbon and PGE graphite, are those are the graphites that are used in the UK nuclear reactors. So in particular, for carbon graphite is used as a moderator and a structural component in the currently operating advanced gas-cooled reactors in the UK. That is providing about 15% of the electricity to the UK nationals at the moment. And then these graphites are life-limited because they're in the core of the reactor, so you couldn't replace them. That's why it's important to study the fracture and the damage of this material. But it's not a simple material. That's what the graphite looks like inside the core. We're looking at about 10-meter diameter here. They're like a hollow in the middle, they stack together. They're about 3,000 bricks in one reactor. If you look at the microstructure, it's porous and has particles. We call it onion-shaped circular particles inside the matrix. It has pores all around, so it's heterogeneous. The challenge is not completely brittle. If it's pure graphite, it's brittle, but this type of graphite, because of the porosity and the particles, is actually quasi-brittle. So we have to decide at which length scale we need to measure the mechanical properties, and how can we actually feed these measurements into modeling to predict what's going to happen at a real component in the reactor. Most importantly, why I'm using small-scale testing, because for civilian samples from the reactor, we don't have many materials, so they're very small, millimeter scale. The technique, what I use here is based on a dual beam workstation, focused iron beam milling. So if I look at this is a block of material, I make 2 trenches from one direction, 45 degrees, then I make another 2 from the other direction. So have left a small cantilever in the middle, so it's square cross-section, and then I have an in-situ loading probe in the SEM chamber. I can load the small-scale sample, which is about 2 by 2 by 10 micrometer, that type of length scale. And you can measure the displacement from the SE images, and the probe can tell you about the loading data. I start with vitreous carbon foam. So the main concept in this presentation is really about you use small-scale measured mechanical properties and to build it up to a macro scale. It's a multi-scale approach. I use this carbon foam here as an example to show you. For example, this videos is a foam structure, and we're looking at centimeter scale here. You load it up, and when you make it smaller, you can see the ligament. And then for lower level or lower scale testing, you take one of the ligament and pull it and make the testing. And then what I did, again, is that I take one of the ligament, put into the SEM chamber, make small cantilevers on the side. Then that is the real property of this carbon. And then if you put it into your modeling, that's the input parameters you need to put into your modeling. So that was the cantilever look like from one of the ligament. Because this carbon is disordered, it's very brittle, so that I measure the different size and different aspect ratio to calibrate my technique. Here's a typical load displacement curve. It always fractures brittle. So you can see the brittle fracture mode, and you calculate the elastic modulus and the flexural strength. Actually, it's the same behavior and a similar value as what you measure from a macro scale. So that means that this technique is trustworthy and also calibrated on single crystal silicon. So that gives me the basis for my future data. If I look at filter graphite, this is a graphite which is simpler than the nuclear graphite. It doesn't have the onion particles. So this is optical image. You can see the matrix. That's the big pores in it. The porosity in this filter graphite is about 52% in volume. So, but if you look into the matrix, there are micropores, and that's a big cross-section to see into the volume. It is not solid. It then has micron and submicron porosity. So that is a tomography scan of a 20 by 20 by 20 millimeter cube. So that is the porosity structure of the sample. I did microcantilever testing on the matrix of this material. So that's typical of the cantilever. You load it up and you see the load goes up nonlinear. Then the fracture is a progressive kind of fracture of ligaments. In general, if I plot the data, the flexural strength, I measured from the cantilevers, and they are very high numbers from 2000 to 600. And this is the number you usually get from a millimeter, from a centimeter or meter scale type of macro size sample. So here is the elastic modulus. It's again much higher at this small scale testing that these type of samples means that the micropores has a different mechanism of the failure of macro scale using those large samples. The second material called carbon graphite. This is a virgin graphite that hasn't been irradiated, but this is from the stock material from the current reactor graphite. Optical image is showing matrix. You can see the circular pores, and those are the porosity. Again, if you focus on the particle in the center, dig in, it's not pore-free. If you focus on the matrix, dig in, it's again not pore-free. So I did a similar test, microcantilevers from these type of regions with porosity. Again, the elastic modulus has a very large scatter, and it changed from about 20 all the way up to 60, 67. And the flexural strength has about high value about 1 gigapascal, and the real and the normal large samples has about 20 megapascal value. So this tells us that for this type of sample, if we input this mechanical property into your modeling, this is really the data you need, and that's the data you output from your modeling. Now I go on with the PGA. They call it piled grade A graphite. This is a irradiated graphite from Magnox reactors. These graphites are radioactive. As I mentioned earlier, we only have a small piece of the material. That's why we couldn't test at a very large scale. For comparison, that this is the matrix without irradiation, but after irradiation, there are lots of pores introduced in the matrix. This is because in the UK reactors, we use carbon dioxide, and that causes lots of material we call lose weight. The graphite lose weight during the reactor service. Again, if you use foxine beam cut into the solid regions, you can see the porosity we saw before. Before the irradiation, the pore has disappeared. Again, you see some lots of deposition. This is too much in detail, but I'm just trying to show that there is a microstructure change after neutron irradiation. Again, if I focus, this graphite has particles. These particles are around the edge, but the difference between this graphite and the carbon graphite is that the particles are needle-shaped, elongated. The carbon graphite I showed earlier has circular pores like onions. The cantilevers are made are from the edge of the particles. You can see also here, there's a bundle of particles sticking out, and that's where the cantilever is. Again, I am able to make cantilevers out of the matrix as well, so that trying to see after irradiation, does the particle and the matrix, do they give the same value or do they react differently to neutron irradiation? So here quickly, just showing one example of the irradiated filler particles. If I look at the load displacement curve, it goes up linear, then it's non-linear. when there was a fracture happened, I saw the fracture from the SEM, but the load doesn't drop, it carry on going. I don't want to overinterpret the data, but this tells us that after irradiation, graphite somehow becomes more resistant to fracture. So this is a fractured surface of this one of the cantilevers. You can see different contrast phases exist. So here shows you a typical cantilever being loaded to fracture because of the existing defect. For the failure particles, I made the cantilevers along different orientation of the particles, so you can actually predict this fit into these computer models. For the matrix, that's another cantilever, you can see it goes up a linear plateau, then linear again, this type of fracture. But most importantly, let me compare that the unirradiated sample and irradiated failure particle, irradiated matrix, it found that after irradiation, the failure particles becomes more stiffer and the matrix becomes softer. This is very important finding, and that's the first time ever actually we are able to separate the particles from matrix. So this also tells you why microcantilever testing is very important. It measures the local properties. And also observation tells you where the fracture actually happened. We're trying to understand what does irradiation does to the matrix material. This is a previous work published by Herdis et al. It's again in FIB. We made a wall in the middle, and then the sample was moved towards a probe. You can see that deformation created on the wall. That we think there's a twinning happening after irradiation, but this was not observed in the graphite. We call it virgin graphite. It doesn't exist in. So that means neutron irradiation has created some sort of damage and a change to the material property. Lastly, this is just some recent quick experiment. So people always argue with me that the cantilevers are made too small because there are lots of pores in the middle. That's why the data is very scattered. So what I did, another thing, is in situ testing in an SEM chamber using a nano indentation. So these tests are on very large samples. Large sample, I mean, it's about 200 micrometer in length. So that's one scale up. That's the diamond tip is flat, and it breaks the cantilever. So this in situ testing, you can tell you it loads up, and you can see the deformation at the same time. The diamond has a flat tip, so it doesn't indent into the material. Most importantly, you can see the whole curve. The graphite is really quasi-brittle. It goes up linear, non-linear, then there's a fracture, progressive fracture afterwards. Interestingly, after remove the load, the cantilever always bouncing back, although there's a large fracture, more than half of the section already. I observed this as well in the smaller cantilevers, about 10 micrometer. Still trying to understand why. Probably because there's some sliding that pulled the graphite cantilever back. Again, that's the in situ testing. Afterwards, we have to cut the cross section to see what's really happening, what the fracture the section is. This is the root of the cantilever. You can see the crack is not straight, it's tortuous. And when look at the surface of the cantilever, it contains so many pores. So it will be able to give us a good average of the porosity, the small scale porosity. Of course, what we did it was like using the FIB cut the cantilever off and measure the cross-section size, so that will be able to fit into computer models that we can predict and calculate the mechanical properties. Right, basically that's all I was trying to talk about today. Rather than focusing on the technical details, I've done an overview of the several types of graphite. I've looked at it. So that means that the microcantilever testing, in situ testing, is very trustworthy because I calibrated all sorts of on vitreous carbon and silicon, a single crystal silicon. And then using this technique, we're able to look at further details on nuclear graphite, and we're able to tell people more about how neutron irradiation does to the mechanical properties, to the particles and the matrix. A larger cantilever is very necessary because it bridges the gap that fit in the multi-scale concept. Finally, I would like to acknowledge the financial support from my project. and also the other two authors from their own projects. Thank you very much.